Let's go ahead and begin. Today we're going to be talking about basic electrical quantities. And so really, I'm just going to be providing you with more formal definitions for the things that you already know a bit about, like voltage, current, power, and energy. And I can't talk and spell at the same time, apparently, my bad quantities. There we go. All right. So would you guys prefer to speak about voltage or current first? Voltage. Okay. So voltage is usually the answer that I get because that's the quantity that you guys are probably a little bit more familiar with. Okay. So the first thing that I'm going to do is I'm going to hit you guys with a mathematical definition. I want you to understand that we are literally never, not even once, going to use the mathematical definition that I'm about to give you. Instead, it's going to serve as kind of a jumping off point for us to understand what voltage means in the context of electrical engineering, okay? So it is perfectly acceptable that you guys do not understand this weird, wacky line integral I'm about to hit you guys with. In fact, some of you may not even be aware of what line integrals are yet. Excuse me. So we're going to define mathematically voltage between 2 points A and B in a circuit as the integral from point B to point A. And I'm using these particular bounds from B to A to get rid of a negative sign that exists in the field theory equation of an electric field vector E dotted into some differential line element dl. Okay. So how many of you guys have had physics 202? Handful of you, right? So what is an electric field vector? So whenever we have some sort of separation of charge, there exists an electric field that is directed outwards from a charge. Whenever we have like charges, so both positive, we have repulsion, and whenever we have charges there where we have like one is positive and one is negative, we have an attractive field between them, okay? So not expecting you guys to understand a whole heck of a lot about electric field vectors or anything like that, but voltage is simply defined as the electric field vector dotted into some differential line element dl, which is just a small portion of the path going from B to A. Now, this is a bunch of gobbledygook for 90% of you guys, okay? So I'm going to introduce something else related to field theory, and it's somehow going to make things a little bit better. Okay. So for those of you that have had physics 202, you may be familiar with an equation for electrostatic force called Coulomb's law. And the equation for electrostatic force is pretty easy. It's nothing more than charge Q multiplied by our electric field vector. So if we substitute this electrostatic force relationship into our voltage equation, we're going to have to do a little bit of algebra. What we're going to wind up getting is 1 over Q times the integral from B to A of our electrostatic force dotted into our differential line element dl. Now, arguably, this might look a little bit worse, but it's better because I'd be willing to bet that at least most of you have some idea of what the integral of a force dotted into a distance is. What's force times distance? Work. That's exactly right. It is literally just work. So what this mathematical representation tells us is that voltage is nothing more than the work done per unit charge, because we have 1 over Q, required to move charge between 2 points in a circuit. So that's all a voltage is, okay? So that's our first definition. The amount of work per unit charge needed to move 1 coulomb of charge from point B to point A in a circuit. So I like this particular definition because it's very fundamental, and it also reminds us that whenever we have a voltage, we have some work being done, and therefore we have to have some energy being transferred. And that's pretty important, okay? So anytime we're talking about a voltage, in the back of your head, think about energy transfer is happening. Okay, so our next definition for voltage is going to come from this exact same equation, but it's really coming from the fact that first, the electrostatic force is a conservative force. And second, it's coming from what the definition of a line integral means whenever we're dealing with conservative quantities. So whenever we're dealing with a conservative quantity, like an electrostatic force, line integrals become path independent. You guys may remember this from one of your math classes. I don't remember which calculus class it is because I'm an old man and it's been a hot minute, but does that sound loosely familiar? Great. So another way for us to interpret this mathematical expression is that voltage is just the difference in electrical potential energy between 2 points in a circuit. Okay. So let's see if we can make sense of this in a couple of different ways by our prior knowledge of engineering, okay? So first, let's try to wrap our heads around the concept of electrical potential energy by thinking about gravitational potential energy, right? You guys have all have some fundamental understanding of what gravitational potential energy is, right? Should be an equation, I believe it's just mg times h. So mass times the gravity times the height. So when we're measuring gravitational potential energy, the difference between, let's say, the surface of this table and this height means that my stylus here has some fixed amount of gravitational potential energy because I've raised it above that surface. Well, I'm using this surface as a reference point, but I could use the ground or the center of the earth or something like that. Well, we can do a similar thing with electrical potential energy, okay? So we're just going to have some spot in our circuit, which we are going to call ground, and we'll get into this more in a bit, that's going to serve as our reference points for all electrical measurements, okay? So the potential energy that we are measuring in a circuit is usually just measured with respect to some ground. So if ground is our zero and we measure something else as, let's say, 5 volts. And that means that the difference between ground and that point in our circuit is 5 volts of electrical potential energy. Now, where you guys have done things like this is literally anytime you use your multimeter. The black lead on your multimeter is serving as your reference point, and the red lead is the high potential energy point. And you're literally just measuring the difference in electrical potential energy between those 2 points with your multimeter. That's exactly how they work. So this isn't anything remotely new. You guys have actually been doing this and applying this particular definition of voltage every time you've used the voltage setting on your multimeter for the last year or more. Okay, so any questions about voltage fundamentally? So nobody has any questions about the units or anything, because I just noticed that I forgot to introduce. So let's talk about that really quickly. Okay. So the units for voltage are the volt with a symbol of V, which I'm sure you guys are all aware of. And fundamentally, a volt is defined as 1 joule per coulomb. And if we look at our mathematical definition, that exactly makes sense, because we know that work or energy is measured in joules, and then we have our expression for work multiplied by a factor of 1 over charge, which we know is measured in coulombs. So a volt is nothing more than a joule per coulomb, which I think you guys are already aware of, but now we formally know why. Okay, so let's talk a little bit about how we are going to represent voltages in circuits in this class. So let's start with some generic circuit element. Let's just call it circuit element A. Okay. And the first way to represent a voltage that I'm going to introduce is what I'm going to call the American style. Okay. This is the one that I'm going to use 95-ish% of the time. Okay. So in an American style voltage representation, we have some magnitude. So I'm going to denote a magnitude over here of VA. Okay. And out to the side, I'm just going to make up a number. So if I were to put 1.5 volts here, this device that is represented by the generic circuit element A might be a AA battery or something like that. Okay. So we have a magnitude, but we also need to indicate a specific polarity. And all the polarity is doing is telling us which side is at a higher electrical potential than the other side. So we do that by indicating that one side is at a high potential using a plus sign, and the other sign is at a lower potential by using a minus sign. Most batteries and things like that literally have a plus and a minus sign printed on their housing, okay, to indicate which one is the positive polarity terminal and which one is the negative polarity terminal. For things like resistors, capacitors, and inductors, they don't typically have a marking because they can operate independent of polarity, and the polarity is just whichever side happens to be, the positive polarity is just whichever side happens to be at a higher electrical potential energy at any given time. We'll unpack that more in a little bit. So if I were to define a voltage VA prime with positive polarity on bottom and negative polarity on top, so the opposite polarity of how I defined VA a moment ago, what would the magnitude of that voltage be? Negative 1.5 volts, right? So if you guys ever measured a negative voltage with your multimeter, what did you do to change that voltage to a positive voltage? You swap the leads, which is literally just swapping the polarity of the voltage that you're measuring. Okay. So if you're ever working on a problem, and I know some of the web work problems and stuff like that are really pesky and they like to just throw random negative signs all over the damn place. If you ever have a problem where you're given a negative voltage and you want to convert it into a positive voltage, literally just swap the polarity signs and you're good to go. Okay. So this is the American style of representing a voltage on a schematic diagram. So now let's introduce the European style. And I'm introducing this style only because you guys may choose to go watch YouTube videos or something like that from somebody else, and they may use this particular representation, which I personally hate. But just so that you're aware of what it is, I'm talking about it here, okay? So here we have our European style. And in the European style, we still have our magnitude, but instead of using a plus and a minus sign to indicate the polarity of the voltage, they instead use a curved arrow, where the head of the arrow is pointing towards the positive polarity terminal, and the tail of the arrow is at the negative polarity terminal. Now, the reason why I don't like the European style, other than just being an American and thinking Europeans are dumb, is that currents to me are usually associated, or excuse me, arrows to me are usually associated with currents. And so having a schematic symbol with a curved arrow and then a straight arrow just doesn't work in my brain when you're trying to represent both the current and voltage across the particular element. So I don't care for the European style, but it does exist. Now you're aware of it. If I wanted to have VA prime be the opposite polarity, then I would just have the arrow in the opposite direction. The last way of representing voltages that we're going to talk about in this class, and we will use this or a modified version of it in a couple of weeks, is what's called the double subscript notation. So when using a double subscript notation, typically our terminals, our nodes, are labeled. So I might label this top node with a lowercase a, and this bottom node with a lowercase b, and then I would indicate my voltage as VAB, where the first letter in the subscript corresponds to the positive polarity terminal of the device, and the second letter in the subscript corresponds to the negative polarity terminal in the device. So from that, VAB prime, which would be the opposite polarity representation of VAB, could simply be written as VBA, where now the bottom terminal is the positive polarity and the top terminal is the negative. So these are the different ways that you'll see voltages represented in this class. Before we move along and talk about voltage sources, does anybody have any questions about this? All right. So there are several different voltage sources that we might see throughout the various points in this class. I'm going to start with the one that you guys are familiar with. So it might look something like this. And this is the schematic symbol for a battery. So we're going to represent the magnitude of the voltage with this symbol VDC. And I want to be clear here. Actually, let me go slightly further. Let me erase that lowercase DC and put a capital DC. So when I use capital letters, that typically means that I'm talking about DC or time invariant quantities. And when I use lowercase letters, I'm going to be talking about AC or time varying quantities. Okay. So in a battery, the long line is the positive polarity terminal, and the short line is the negative polarity terminal. Now, this symbol that I've drawn here is technically the symbol for a multi-cell battery. So something like a car battery that is composed of several smaller cells connected together to give you some overall larger battery module. Where a single cell battery like a AA or AAA or something like that typically only has one long horizontal line and one short horizontal line. And you probably saw that very often in the Engineering 120 series. The reason why I don't like that symbol is because it could be confused with the schematic symbol for a capacitor if you weren't paying enough attention, where the schematic symbol for a capacitor is just two horizontal lines. So instead of representing voltages or DC voltages with batteries, like was done in the Engineering 120 series, I'm going to just use a generic DC voltage source symbol. So that's going to look something like this. So we're going to have a circle, and then there's going to be a positive and a negative polarity terminal defined by the plus and minus sign on the symbol diagram, like so. So this is just a DC voltage source. And a battery is effectively just a special case of a DC voltage source. So where might we see voltage sources or DC voltage sources that aren't batteries? Well, there are, I think, 12 of them in this room. If you look around the edges of the room, there are 4-channel DC power supplies that we are going to be using in most of our labs. This is the technically correct schematic symbol for those devices. It's the white box with 3 knobs on the left-hand side, 3 knobs on the right-hand side, and a whole bunch of little ports on the bottom for those of you that are looking around the room trying to figure out which piece of equipment is the DC supply. Another thing that we're going to see, this will be a bit later on, is an AC voltage source. So we have our circle with a plus and minus sign to indicate the polarities. And then I'm going to put a tilde here in the middle, which represents that the voltage is changing in time. Okay. So for my magnitude, I'm going to have lowercase v, lowercase ac, and that will specifically also say that it's a function of time so that we know that things are changing, like so. So this is our symbol for an AC voltage source. And these 3 voltage sources are examples of what are called independent sources. So what the independent source means is that the voltage that is provided by these sources is fixed and does not matter what the source is connected to. So if you hold a battery in your hand, it provides some amount of DC voltage. And if you connect that battery to a circuit, it arguably provides that same amount of DC voltage until it discharges and all of that kind of good stuff, okay? So an independent source does not care about what it's connected to. There will be a specific potential difference between those 2 points in the circuit, regardless of what is connected to the terminals of those batteries. Now, in contrast with those independent sources, we're going to have 2 dependent sources that we're going to look at as well. So we're going to differentiate between an independent source and a dependent source by using a diamond. Because it's a voltage source, I'm going to have a specific positive polarity terminal and negative polarity terminal. And I'm going to choose for this particular source to be what's called a voltage controlled voltage source. Okay. So the magnitude or the amount of voltage provided by the voltage controlled voltage source is going to be expressed in the general form K times some external voltage Vx, where K, this scaling factor, has units of volts per volt, or effectively unitless, unless you are told otherwise. Okay. So in a voltage-controlled voltage source, the amount of voltage that is provided by this device depends on some voltage Vx located elsewhere in the circuit. And then that voltage Vx is scaled by some particular factor. So if Vx is 2 volts and the scaling factor is 3, then this guy provides 6 volts. If the voltage Vx is negative 4 volts and the scaling factor is 1/2, then this guy provides negative 2 volts. Okay, it is literally just multiply the scaling factor by whatever the voltage Vx is, and Bob's your uncle, you have the voltage provided by this thing. We also have a current controlled voltage source. Okay. And the symbol for this is literally identical to that of the voltage controlled voltage source. It's just a diamond with a positive polarity terminal and a negative polarity terminal. So the way that we're going to be able to tell the difference in a schematic diagram between a voltage controlled voltage source and a current controlled voltage source is by the magnitude. So we might have something that looks like, and I'm going to use this scaling symbol as a lowercase g. Actually, I messed that up, lowercase r times some current Ix, where our scaling factor r has units of volts per amp. So that if a current Ix of 3 amps is flowing, And our scaling factor R is 2 volts per amp. Then 2 volts per amp times 3 amps gives us a 6 volt output for this device. Okay. So these are dependent sources. And they are used in practice to model the behavior of amplifier circuits and things like that, or components that are used as amplifiers, like MOSFETs, bipolar junction transistors, and all of that kind of good stuff. Okay? So you can't really go buy a voltage controlled voltage source or a current controlled voltage source off the shelf. They are actually circuits in and of themselves. But from an analysis perspective, we can treat them just like anything else, and they'll pop up and bite you in the butt very regularly in this class. All right, so any questions regarding the different voltage sources that we are going to see? Okay, so let's now talk about current and charge. So we'll start with our mathematical definition like we did for voltage. So current I, as a function of time, is defined as the change in charge with respect to time. So if we looked at the units of this thing, I'm going to do this first so that I don't forget about it again. The unit of current is the ampere with a symbol A. And fundamentally, it is nothing more than 1 coulomb per second. So literally just charge per time. So if we wanted a definition for current, what does that derivative tell us? So particularly a derivative with respect to time. What does that mean? We're looking at a rate of something that's happening, right? So we're looking at the rate at which our charge changes effectively. So current is simply the rate at which charge passes a particular point in a circuit. Now, we can mathematically rearrange this derivative expression for current to find charge for a known current, okay? So charge, Q of t, can be expressed as the integral from T naught, where T naught just represents some point in time where the amount of charge is known, to T, some later point in time that we are interested in, of our current I of T prime dt prime. So let me explain what this prime notation here means. I'm not trying to blow anybody's mind or anything. So one thing You've probably taken a math class before where they use the prime notation to indicate taking a derivative, right? I will never use that in this class. Prime never means take a derivative in circuits one. Okay. Instead, what I'm trying to indicate here is that I'm using a dummy variable. Okay. So I can't integrate with respect to t and have t in the limits of my integration. That would just be too damn confusing. So instead, I'm using t prime to represent time in my function, and then the limits of my integration are where that variable t is coming. Okay, so all it is just a dummy variable representing time. Okay, you could just as easily call it x. Typically speaking, you would use the Greek letter to replace it, but we can't use tau in electrical engineering, which would be the Greek representation of lowercase t, because that has a special meaning, and so it'll just mean that we'll get confused later on. So I'm just choosing to use t prime as my dummy variable here. Now we need to add one more thing to this expression, and that is what's called an initial condition. So since we're evaluating from t naught to t, we have to add to this expression the charge at that point in time, t naught, where charge is measured in coulombs. So let's work a quick mathematical example here. Okay. So let's say that I have some generic circuit element, and these ellipses are just representing the fact that this is part of a larger circuit. And my current I of t is flowing down through this device. So if I of t has the following waveform, so let's say that our current starts at 0 amps and increases up to some point, stays constant for some amount of time, and then decreases and then stays at 0, like so. Let's define some things. So let's say that the maximum value of the current is 2 amps. It goes from 0 to 2 amps in 1 second. Actually, let's make that 2 seconds since it's 2 units of time. This point represents 5. This point represents 8. And let's also say that Q at 0 seconds was 2 coulombs. I want to find the total amount of charge that has passed through this element from 0 to 5 seconds. So which of the two equations that I gave you guys above is the one that we need to use? Let's start there. So the first one or the second one? Yeah, it's the second one. We're trying to find charge, and we know what the current is doing. So it's the second one. That's not supposed to be a trick question by any stretch of the imagination. Just historically, students have picked the wrong one. Okay. So realistically, sorry, we could simply apply this integral. So to do that, we would define this function as a piecewise function, right? So we could say that I of t looks like, let's see, so it has a slope of 1 amp per second over the interval from 0 to 2, right? So that's just going to look like t for 0 is less than t is less than 2 seconds. Then it's just going to be a constant value of 2 amps for 2 seconds is less than t is less than 5 seconds. Then it's, let's see, it decreases 2 in 3 seconds. So that's going to look like negative 2/3 t minus 5 plus 2 over the interval from 5 seconds is less than t is less than 8 seconds. And then let me expand this thing a little bit. 0 amps for t is greater than, 8 seconds. So I'm sure some of you are looking at that expression, negative 2/3 times t minus 5 plus 2, and you're going, where the hell did he get that from? So let me explain things really quickly. You guys should have learned this, or let me rephrase that. I think you should have learned this in your pre-calculus classes, but whether or not you did is an entirely different bag of cats. All I've done is effectively time shifted things 5 units to the right, which is why I have that t minus 5. My slope is negative 2/3, and my y-intercept, so effectively where my line is at t is equal to 5 is 2 amps, which is why I have that plus 2. So lots of math went into this. Then we would effectively have our charge q of t would be, the integral from 0 to 2 seconds of t dt plus the integral from 2 seconds to 5 seconds of 2 amps dt plus our charge at 0, which is the point in time where our charge was known. So we're just going to add 2 coulombs. There's nothing wrong with that. In fact, it's mathematically perfectly correct. But I feel like there's an easier way, and hopefully most of you guys do too. So what would be an easier way to find the total amount of charge? Simple geometry, right? We have the area of a right triangle and the area of a rectangle, and we can add those bad boys together, tack on plus 2 coulombs at the end, and we would get the exact same result. So in this class, literally, let's talk about the math that I'm expecting of you. Okay, this is as good of a time as any. You need to be able to do the derivative and integral of simple polynomials. So like, x squared, x cubed, that kind of thing, and combinations of those. Sine and cosine functions, exponential functions. End of story. That's it. Everything else is going to be simple areas or derivatives of shapes made up of triangles and rectangles. So, as quote unquote difficult as this class is supposedly is, the math that goes into it isn't the hard part. It's understanding the analysis and applying all of that kind of good stuff to circuits. So let's do this problem the lazy way. What's the area of this right triangle? So let's start by, how do you find the area of a right triangle? And I'm not trying to be insulting to anybody, but I taught a circuits class over the summer several years back where literally over half of the class did not know how to take the area of a right triangle. So let's prove that you guys are way smarter than that bunch of students. Somebody tell me what the area of a right triangle is. 1/2 the base times the height. All right, so we have 1/2. Our base in this case is 2 seconds. Our height in this case is 2 amperes. So we have 2 amps times 1 second. So what's 2 amps times 1 second? So we have amps times second, so I'm not sure how we're going to get amps per second anywhere. What's an amp times a second? A coulomb. So this looks like 2 coulombs. Now for the hard part. How do I find the area of a rectangle? I mean, I can't help but notice that none of you have told me. Just the base times the height, right? So our base in this case is 5 seconds minus 2 seconds, or 3 seconds. Our height is 2 amperes, so I think this comes out to be 6 coulombs. So here we have 2 coulombs, here we have 6 coulombs, here we have 2 more coulombs, add those together, and we get 10 coulombs. Doesn't have to be much harder than that. This is legitimately a test question. All right, so any questions on current and charge conceptually? Yes, sir.
So on the I equals T, can you explain the beginning of the third line from 5 seconds T to 8 seconds, why you wrote that first part?
This bit right here?
Yes, sir.
Sure. So I'm putting things in the y is equal to mx plus b format for just a straight line, because over that interval we have a straight line. The negative 2/3 represents the slope of that line, right? So its height changed by -2 units over an interval of 3 seconds. So that's why we have -2/3. I have t minus 5 because I've time shifted that line over 5 seconds from the origin. So whenever I shift to the right, I have t minus. If I time shift to the left, I have t plus. Since I shifted over 5 units, that's why it's t minus 5. The +2 comes from the fact that the y-intercept after our time shifting is at 2. So if we treat t is equal to 5 seconds as our new origin, the y value at t is equal to 5 was 2 amps. So that's our y-intercept.
Okay.
So it is literally just the y is equal to mx plus b format, except that I've shifted a line by 5 time units to the right. Yep. Okay. Any other questions? All right, so let's talk about representing currents. And luckily for us, there's literally only one way to do this. So if we have a generic circuit element A, like so. Our currents are going to have a magnitude. So I'm just going to call this current IA. And we might say that IA is something like 2 amps. Well, the other parts to fully define a current is a direction. So I'm going to say that IA is 2 amps down. So if I had a current of IA prime direction up, what would the value of that current be? Say it louder, Ashley. -2. So if I'm ever dealing with a negative current that I want to make positive, I just swap the direction of the arrow, and that gets rid of the negative sign. So that's how we represent currents. Yes. Okay. All right, so lastly then, we need to talk about current sources. So let's start with a generic DC current source. So we have a circle once again. The arrow indicates the direction of current flow. And then I'm using capital letters to represent that this is a DC quantity. Okay, pretty straightforward. Here we'll have our AC current source. Same symbol, except that there's a tilde in the middle of it to let us know that our current is changing in time. And then our magnitude would be represented by IAC as a function of time, all lowercase. These are our two independent current sources. So they provide a fixed amount of current regardless of what they are connected to. Then over on the right-hand side, let's put our dependent current sources. So dependent sources are always designated by a diamond. So let's start with a current-controlled current source. So we're going to have K times some current IX, where in this case, our scaling factor of K is measured in amps per amp, or a unitless quantity. So if IX is 2 amps and K is 3 amps per amp, then we get a total output current of 6 amps for this device. And we also have a voltage controlled current source. Where our scaling factor has a symbol of G. And so we're going to have G times Vx, where our scaling factor has units of amps per volt. So it effectively converts a voltage into a current. All right, any questions on current and charge before we move on to our last set of relationships regarding power and energy? All righty. So Let's start with our mathematical definition of power. What's power in an electrical circuit? IV, current times voltage. Absolutely right. Still the exact same thing as it was before. So voltage times current. From this, so we can say that the unit of power is the watt, where a watt can be defined as 1 volt times 1 amp. We also know that power is related to energy. So that's going to be 1 joule per second. Let me move this unit thing over so I can go ahead and give you the relationship with respect to energy as well. So power is the derivative of energy with respect to time. Energy is then the integral of power. And I'm going to define the limits of my integral as from T1 to T2, which is just 2 points in time we happen to be interested in. Where energy is measured in joules. So for our word-based definitions for power and energy, they're going to be related to each other. So it's kind of circular reasoning, but it's the best that I can do. Power is the rate at which energy is transferred in a circuit. And energy is the total amount of power transferred over an interval of time. All right. So let's talk now about the passive sign convention, which this is a topic, and I'm going to sound like more of an egotistical ass than I normally do, which that's a pretty damn high bar. This, in my opinion, is a pretty simple and straightforward concept that for whatever reason seems to confuse the hell out of students. Okay. So I am going to try to explain this in the simplest and most straightforward way possible here. Okay. So passive sign convention. So let's say that I have a generic circuit element A. I'm drawing these big long terminals like so for reasons that you'll see in just a moment. And circuit element A is part of some larger circuit. Okay. Let's define the voltage drop, across element A as having the positive polarity on top and the negative polarity on bottom, like so. And let's say that our current IA is flowing into the positive polarity terminal and therefore out of the negative polarity terminal. So in this case, we could say that the power absorbed by element A is the product of VA and IA, and the power supplied by element A is just negative VA times IA. So supplied power is just the negative of absorbed power and vice versa. Now, let's consider a case where we have some circuit element B. Once again, this is part of some larger circuit. We're going to define the voltage drop across element B as positive polarity terminal on top. But now I'm going to define the current that's flowing into element B as flowing into the negative polarity terminal. In this case, the supplied power is VB times IB, and the absorbed power is negative VB times IB. That's the passive sign convention. I legitimately do not understand why this confuses people, because it is just easily stated as when your current is flowing into the positive polarity terminal, voltage times current is absorbed power. If the current is flowing into the negative polarity terminal, voltage times current is supplied power. That's it. Now, I want to be clear here. I did not in any way, shape, or form put any constraints on whether VA, IA, VB, or IB were positive quantities or negative quantities, because that literally doesn't matter. If the current is flowing into the positive polarity terminal, the product of voltage and current is absorbed power. If the current is flowing into the negative polarity terminal, the product of current and voltage is supplied power. That's it. Doesn't need to be any harder or more confusing than that. All right, the very last thing that I want to talk about is Telegen's theorem. Telegen's theorem states that the total amount of absorbed / supplied power in a circuit must sum to 0. So if we compute only absorbed powers, all of them have to add together to 0. If we compute only supplied powers, all of them have to add together to equal 0. And if we have a combination of absorbed and supplied powers, They all have to add together to equal 0. This is nothing more than the law of conservation of energy. But some other guy got their name associated with it. Good for him. That's it. All right. So that's all I wanted to talk about for today. So we have 45 minutes remaining in class. There is an in-class assignment that is available on Canvas. There is also the mini lab. I would encourage you guys to do the mini lab first, and then whatever time is remaining after you complete the mini lab, work on the in-class assignment. Just to remind you, the in-class assignment is not graded for completeness or correctness. So if it takes you 30 minutes to do the mini lab and then you only have 10 minutes to work on the in-class assignment, that's okay. Just turn in what you got and I will accept it. If you choose to complete the in-class assignment, I don't have it set to be due until 8 a.m. on Wednesday. So it's due right before our next class meeting starts. I'm not telling you to complete it. I'm saying if you choose to, that's your prerogative. It's not due until then. All right. If you have any questions about stuff, let me know.